Now, when we're talking about the gases, it's important to look at volume, pressure, and temperature. And so, we're looking at, the state of that system, and we're looking at, what's going on with that gas. And we're going to deal with gases that aren't too dense. And so we're dealing with ideal gases that are not too dense, and they obey the ideal gas law relationship that we're going to look at. So with this one here, K5a, let's say that we have an ideal gas, and let's take a look at the properties of this gas, with an ideal gas. So it cannot be liquefied or solidified. And so, like real gases, and molecules obey the laws of mechanics, and so they obey Newton's laws. The molecules are point particles, and they each have negligible volume. And when they collide with the walls, the collisions are elastic. They're elastic collisions. The molecules have a range of speeds, and they move randomly as well. And so this is true. All these are true with ideal gases. And a real gas may be approximated by an ideal gas as long as the density is low. And so if you have too dense of a gas, it's not really going to obey what's going on with the ideal gas law here. Okay, so if you want to pull up the simulation, you can go to PhET and then go to gas properties. And then let's take a look at what would happen to pressure if volume is changed but the temperature remains the same. And so when you do that simulation and you try that, you can see what happens. And what you'll see is what happens in one of these properties that we're looking at, gas properties. And so go ahead and pause the clip, give that a try, and when you're ready to learn more about that, you can hit play, and then we'll take a look at it here. Okay, so with Boyle's law then, we're dealing with an inversely proportional relationship. The volume and the pressure, as long as temperature is constant, is inversely proportional. So in other words, as the volume gets bigger, right, as we get bigger in volume, pressure is going to drop. And as pressure drops, if we keep temperature the same, that's what will happen there, and that's Boyle's law. So volume is inversely proportional to pressure in Boyle's law. What we're going to be using for volume is meters cubed, and then pressure is going to be in newtons per meter squared. And then also pascals. That's what 1 Newton per meter squared is, 1 Pascal. All right, so let's go ahead and apply this. This is K6. Ideal gas is in a sealed container with a movable top. The chamber has a heating element and allows the temperature to stay constant as the volume expands. Person changes the volume from 125 centimeters cubed to 160 centimeters cubed. If the original pressure was 3 pascals, what is the final pressure? So when we set this up, we can draw this out. We know the volume is expanding from 125 to 160 centimeters cubed. The original pressure is 3 pascals. We want to find the final pressure. So what we're going to need to do is convert our 125 centimeters cubed to meters cubed, right? So what happens with a cubed conversion, if we just had 125 centimeters, and then we would have, 100 centimeters is 1 meter, right? If we want the cubed conversion, right? Cubed conversion, that's centimeters cubed, so this has to be cubed. The 1 is cubed, the meter's cubed, so we cube everything here. So when we end up getting our value for meters cubed, it's going to be very tiny, and that's going to be the volume there. And so when we set this up, we've got our original setup and then our final setup when we convert both of them. So the original volume is 1.25 times 10 to the negative 4th meters cubed. Our final volume is 1.6 times 10 to the negative 4th meters cubed. And so when we set this up, if we bring this to the other side, right, so PV equal over nRT, the initial state of the gas has to equal the final state of the gas. And it's give and take, right? So pressure and volume, number of moles is N, and then R is the the constant, the gas constant, and then T is temperature. So our gas before should equal the gas afterwards. And so if we consider that, yeah, we can figure out what's happening with the final pressure. So go ahead and use this, place your values in there. Another thing that we're gonna have to pay attention to here, you know, some things can cancel out, right? The number of moles can cancel from both sides. R can cancel from both sides. And so we end up getting a ratio of P, actually both, you know, and R and T, right? Temperature staying the same. So pressure 1 times volume 1 should equal pressure 2 times volume 2. So the initial state of the gas should equal the final state of the gas. It's give and take. And so, yeah, go ahead and complete this one and pause the clip, and when we're ready to check, you can hit play to continue. All right, so we should end up getting a final pressure of 2.34 pascals, and that should make sense because the gas is expanded. Okay, now in this case, what would happen to the volume if temperature was allowed to change but pressure stayed constant? So you can use this gas law simulation again and take a look at this. Again, if you had, you know, temperature is allowed to change, pressure has to stay the same, what would happen to volume? So go ahead and pause the clip, give that a try with PHET. Just go to PHET, P-H-E-T, and then go to gas properties in the website and give that a try. And then when you're ready to explore this more, you can hit play to continue. Okay, so this is Charles' law. What happens with Charles' law? The volume is linearly proportional to temperature. And this is where the pressure stays constant. So the volume is proportional to temperature. So in other words, as the temperature decreases, right, as we get, you know, 200 degrees, 100 degrees, 0 degrees, the volume is getting smaller and smaller and smaller and smaller till theoretically where the volume would be 0, and that would be at 0 Kelvin. And so we know that, you know, we're not going to have 0 volume. Some really weird things happen around absolute 0, and in fact they just went below absolute 0 not too long ago. And so that's significant there with, you know, but this should make sense, right? You have a you know, the volume is getting smaller and smaller and smaller. The temperature is getting colder and colder and colder, so the volume is getting smaller and smaller and smaller as we go to keep the pressure the same, right? Okay. So temperature being Kelvin, volumes in meters cubed, and we can explore that here with that. With the Kelvin scale, the concept of absolute 0 follows that there, where, you know, that's where essentially volume would be 0 and pressure would be 0. We know it's not 0, but that's where the x-intercept is, right, with the y. And yeah, it starts at 0 Kelvin, and we can use our Celsius scale to you know, compensate with that and evaluate that. So the freezing point in water is 273.15 Kelvin, and then the boiling point is 100 degrees higher. Now in Kelvin, you just say that value in Kelvin, right? It's not degrees Kelvin, so 100 higher than the 273.15. You got that there.